Hello and welcome to another video on forces. Specifically, we're going to be talking about ramps today. Thus far, when we've been looking at forces, we've been looking at forces that largely align to the coordinate grid as we know it. X left, right, Y up, down. Now, sometimes the forces would be acting on an object that is on the ground, like so, or sometimes the object would be acting on a force on a wall, like so. And even so, we'd occasionally have forces that go at angles and act at these angles, but we could easily fix that by breaking these into components and simplifying it back down to X and Y values. The problem comes when we deal with a surface that isn't perfectly flat, isn't level. The most common expression for this, the one that we will typically see on the AP exam and where many students struggle, are ramps. Now, in the case of a ramp, the ground itself is flat, but the surface we're measuring or looking at isn't. So if we imagine we have a box acting on a ramp or sitting on a ramp, we can still draw the forces. We can still make the free body diagram. We can talk about the normal force, which is perpendicular to the surface. We can talk about the frictional force, whereas if this block is trying to slide down the ramp, it's going to stop it from moving by acting parallel to the surface this way. We can even talk about the gravitational force, which will always, always, always pull straight down. Let's go ahead and label those. Now this is assuming that there's no applied force or any other forces acting on it, just the three forces we have listed here. Just a box resting on a ramp. And the problem with this is if we draw in our coordinate system or our grid, the only thing that really lines up is gravity. There's these other two angles that we have to break up two vectors on. And worse, we don't know what those angles are. All we know is the angle of the ramp. And we could go and do some very fancy geometry, solve all these angles, figure it all out, but that's long, exhausting, and problematic, and quite honestly, more hassle than it's probably worth. Instead, we erase that coordinate system and we start cheating. One of the key ideas in physics is that any reference frame, any coordinate system you draw is completely arbitrary. It doesn't matter where you draw it, we just draw it to calibrate things, to measure with reference to something. In this case, down doesn't have to be negative. If you're talking about acceleration due to gravity, it could just be 9.8, depending on how your problem's set up. Or in this case, more specifically, force gravity doesn't always need to be in the down direction. It needs to pull towards the center of the Earth, but that doesn't necessarily need to be down. What I can do is grab this entire thing and twist it so that this is flat and that this right angle here can work for us. Because when I draw my coordinate system for this, y, x, instead of having two angles off to the side being planes, I only have one. And through a trick of geometry, or understanding if you prefer, we know that this angle here is the same theta as this one. So now I can split my force gravity up into force gravity y and force gravity x. And using this, we can now talk about inclined planes just as easily as we did objects on flat surfaces. We just sum of all forces x equals max. In this case, it would be force gravity in the x direction minus force friction. And we could do the same thing for y. Sum of all forces y equals may equals force normal minus force gravity y. And solving these is a lot easier, a lot simpler than trying to do multi-angle that we would have had to if we didn't rotate it. So let's go ahead and start taking a look at this. We'll start with the simplest version. Here's the standard simple version of it. I have a 10 kilogram block of wood that I place on a wooden ramp, wood on wood. If the ramp's inclined 30 degrees, does the block move or does it stand still? Effectively what I'm asking is, does the forces pulling it down the ramp, gravity in this case, exceed the maximum static frictional force. Let's go ahead and break this down. So the first thing we're going to do is draw our free body diagram. We're going to have normal force coming up like so. You're going to have the frictional force going off to the side. You're going to have gravity pulling straight down. Connect all the dots. And we want to know, does it move? I could solve it like so, but that's going to be messy. So instead I just rotate it on its side so that my normal force is straight up and down, despite my awful drawing of it. My frictional force is directly to the left, and the only one I have left over is force gravity that I need to split up. Let me fix up my drawings here to make it a little clearer what's going on. Here we go. So now, what I need to do is set up my sum of all forces. You'll notice that this is 30 degrees over here, which tells me that this is 30 degrees here. I can go through the geometry, and I'll go through the geometry in a later video, but for now, just trust me. At this point, we have two directions, which means we need two sum of all forces. So let's say sum of all forces in the x direction equals max. And then we have sum of all forces in the y direction equals may. And then we just need to list our forces. Because force gravity is at this angle here, it's going to be in both the x and y direction. It's going to have a Fg in the x direction component and Fg in the y direction component. So when I write my sum of all forces, let's just put that in. In the x direction, I have Fg in the x direction, the part of it that's in the x direction, this side here, minus the frictional force here. In the y direction, I have normal force and force gravity in the y direction. Now, you'll notice right off bat that these forces may or may not balance. So the first thing we got to ask ourselves is, which way is this box going to accelerate? Okay, if I untilt it for just a second, which way is it going to go? Is it going to go along the x-axis, along the y-axis? Well, if you've ever seen a box on a ramp, or anything really on a ramp, it's going to go down the ramp if it moves at all. So it's going to go in this direction, which, if we retilt it, is the positive x direction. It's not going to go up and down off the table, so we know that my acceleration in the y is going to be 0. I also know that my force gravity is going to be m times g, but the x and y values are a little different. Let's go ahead and grab this and rotate this again. If we rotate this so we can look at our right triangle being here, the right angle is here, and my angle is here, which means FGX is on the opposite side, FGY is on the adjacent side. So FGX will be using sine, FGY will be using cosine. Let's go ahead and find FGX, FGY. For FGX, that's opposite and hypotenuse, so sine of my angle, which is 30, but I'm going to leave angle for now, equals FG in the x direction over FG. Solve for FGX, I get FG in the x direction equals FG times sine of angle, which really means m times g times sine of angle, because force gravity is m times g. Let's go ahead and plug the numbers in just so we can kind of see how this would work. Again, we could always go back and do this symbolically, but for now, 10 times 9.8 times sine of 30, which is 49 newtons. So in the x direction, I have 49 newtons of force. Do the same thing for y. Adjacent side, which is cosine of my angle, equals FGY over FG. Again, solve for FGY, I get FG in the y direction is FG times cosine of my angle, or because FG is just mg cosine angle. Again, we can just plug in our numbers. 10 times 9.8 times cosine 30, which is 84.87 newtons. Now that I have these numbers, I can solve the rest of this problem. I can go back and plug the numbers in. FGY I have here is negative 84.87, which means my force normal is 84.87 newtons. Up here, Fgx is this 49, and then minus my frictional force, which is mu times Fn. If I go ahead and drag this down so it's out of the way, if I go ahead and plug in the values, wood on wood, I go look at my handy dandy table, my reference chart will tell me that this is 0.62. We're seeing if it's moving, so it's static, times 84.87 is negative 3.62 newtons. In other words, the frictional force, the max frictional force, is bigger than the force that the wood block is currently experiencing by about 3.62 newtons, or fairly little in the scale of things. This is not to say that the frictional force will be 3.62 newtons. The frictional force will be 49 to cancel out the 49 we have already. But the upper limit is this. And because the frictional force can go bigger than the current gravitational force, this will not move. This is one of those moments where the math we do is for a limit, not for the actual value, and you have to interpret your answer as such. If, for instance, I had a different angle, maybe it'll move. Or if I had a different mass, maybe it would move. Had you done this symbolically, let's go ahead and step back and do this symbolically instead. So instead of plugging in Fgx, I'm going to put this mg sine theta minus mu times Fn. And Fn, I get from down here, mg cosine theta, or equal to my force gravity in the y direction. So my mass times my acceleration in the x direction was my mg sine theta minus mu mg cosine theta. And now I would plug my numbers in and see if my acceleration gives me a positive or negative value. If it's a positive value, I know that the gravitational force would win out, thus providing me with acceleration down the ramp. If it was negative, I'd find out that the maximum value, the mu static max, is greater than
the gravitational force acting down the ramp.
Just to double check and verify, max equals 10 times 9.8 times sine 30 minus 0.62 times 10 times 9.8 times cosine 30. So it gives me the negative 3.62 newtons for my net force. And there you have it. The general principle for any problem involving a ramp is the same. Rotate it, so that way you have your axes like so. Break your gravity up and then solve your equations. If there's an applied force, you can find that out. As if it's moving, you can use the different value for friction. Okay, thanks for watching. Have a good day.